Start recording. Okay, so last Thursday, we finished with some glycosyl fluorides and talked about activating glycosyl fluorides. And if you remember, I took one look at making them and I said, I will come back to that because I'm not 100% sure. So now I'm coming back to that because, well, I read all the original literature on this and I'm still not 100% sure because it doesn't look like they're 100% sure. But we will walk through what we can do to make some glycosyl fluorides. So, making. So this is going to come back to some of the glycal chemistry that we're going to actually move into later in this lecture. So I like glycals. So again, this is a glycal. And if we treat this with MCPBA, and we're going to come back to this chemistry quite a lot. Sugar chemists love a thing that works, and they keep reusing it. We make an epoxide. And generally, we make that down epoxide. The other reagent we can use for this is DMDO. Now, fine, yeah, we'll walk through both of those because it might have been a little while for some of you with MCPBA, and it might have been a little while, probably has been forever for a lot of you with DMDO. Okay, so if you remember or not, MCPBA stands for metachloroperbenzoic acid. So there's a chloro and it's meta to a perbenzoic acid. And these work by epoxidizing alkene. So I'm just going to draw an alkene there. It's going to be a simple alkene. And the way this works is we're basically going to transfer an oxygen from the MCPBA onto the alkene. I'm just going to re-sketch this, and I'm going to change color of my pens because it's more fun this way. So going back to early chemistry, double bonds are pretty decent nucleophiles. And you have an oxygen-oxygen single bond, and that is a very, very, very labile and weak bond. That's going to create a carboxylic acid leaving group, which is a good leaving group, O- leaving group. I am waving at the camera. My camera is off, so I'm going to turn my camera on so I can wave at the camera. Don't think it really adds anything to the lecture, but I feel less stupid talking with my hands if it's being recorded. I don't know why. But, okay, so we have a carboxylic acid leaving group, CO2 minus, very good leaving group, very stabilized negative charge because the resonance, yeah, I know, it's part of the whole experience. I pace back and forwards normally when I lecture, and here I am sitting in a chair, and it's pretty awful. So we can remake an oxygen carbon double bond that releases the electrons in the other double bond, and we can grab that hydrogen to our suck-ups. Okay. So what does that do? Well, hydrogen can't make two bonds, so let's pop those electrons onto the oxygen. So if we just want to number these, again, if it's been a while, there's an order to those arrows. And that takes us, follow it to its logical conclusion. you get that. That, of course, is not particularly stable because you got a negative charge and a positive charge. That's a pretty decent carbocation. Alkoxides are fine, but not when they're not close to each other. I'm going to arbitrarily draw that the oxygen is on the top face of this molecule is going to snap shut onto the carbocation, also from the top face because it can't do a reach around. There we go. So push one of the other guys down, right stereochemistry. Everybody's happy. I guess there's a hydrogen on here, which is down, but I haven't drawn that. So that's how MCPBA works. So we epoxidize something. DMDO does the same thing. What the hell is DMDO? DMDO is a much stronger oxidation unit. You take acetone. You take something called oxone, which is crazy ass sulfated potassium salt. It does have a molecular formula, but that's because there is an average oxidation state of oxone. It's sulfur with way too many oxygens attached to it, with some hypervalent potassium and a bunch of other stuff in there, and it's this really just super strong oxidizer. I don't quite know what the molecular formula for oxone is. You can draw one, and if you look it up, you'll find something, but it's not accurate because that's not actually how all of oxone is. It's kind of an amorphous mixture of different oxidation states. Regardless, what does that mean? It basically means it's oxygen. We're going to add oxygen. And so it does a weird thing. We are going to add oxygen to the carbonyl of acetone. We get a situation that is very reminiscent of the situation that we just had. Let's snap those shut. Okay. You always make DMDO in situ, like in the solvent that you're going to do the reaction in. You never isolate DMDO. It explodes. It explodes as soon as you look at it. It really, really, really wants to give off oxygen gas. And so, yeah, it just detonates a lot. And what it doesn't detonate, it oxidizes and then sets fire to because it really wants to give off oxygen gas. And so between detonating and setting fire to things, it's a great reagent. But you want to make it, and it's really good if you keep it in solution. It's really not good if you make it too concentrated or you use it in a reaction, forget to quench it. That's also bad. Actually, just got to be careful. Anyways, great reagent, oxidizes shit. Unsurprisingly, if you take a double bond, same one, it shouldn't be too surprising that we can draw some arrows here. Attack the oxygen. Let's break the oxygen single bond because those suck. Nobody likes oxygen single bonds. And now that thing is just silly. Of course, this is a stupid system. Having two oxygens bound to carbon is something carbon doesn't like, especially when one of them is negatively charged. So it is going to delete my page. Nope. Scroll back. Scroll back. Okay, find the mouse. There we go. We will take care of that. And we will generate our byproduct from this, which is acetone. Which, all else being equal, is much safer than DMDO. Well, it's just kind of much safer than DMDO under all circumstances. Just got an email coming in saying emergency plumbing needed. Oh, okay. Okay, yep, that's fine. I will leave it to other people to deal with. Hey, Susanna, it's your lab that's flooding right now. So, with it looks to be fine.
Yeah, I was just going to email Beth.
Okay, John just emailed Beth. So you're there. That's what you were dealing with, eh? That's
Yeah,
a very good reason to miss class if your lab is flooding.
I'm sorry.
For flooding the lab or missing class?
A little bit of both.
Okay. Oh well. I I don't think we'll get anything damaged. At least what didn't happen overnight. Because the problem with that lab, of course, is if we flood it, it drips down onto our other lab. Like, it would be okay if it was somebody else's lab underneath, but it's not. It's ours, and so that's not particularly good. Okay, so epoxides. Awesome. DMDO, you can make other epoxides out of this too. She's just
Sorry,
better at this than you, Paul.
I'll stop being distracting. Sorry.
It's more fun that way. So I'm just trying to remember where I was going with this. Okay, yes. So let's say that we can make. So you can see maybe why DMDO might be preferred, because you only get the byproduct you get out of there is acetone. And what you'll often see with those kind of reactions is we'll do DMDO in acetone. Unsurprisingly, you make it in acetone by just controlling the amount of oxone that you add. And then once the reaction is over, you can bubble in something like isoprene gas. And that's just going to consume the remaining DMDO. Or you can add dimethyl sulfide. And just like with ozone, you will make DMSO out of that. Another safe way to get rid of any excess DMDO that is in your reaction mixture. But we take DMDO, we take that. There's no byproducts. You don't have any of these salts that you have with all these other oxidizing agents. If you think about almost anything else, like even MCPA, if this perbenzoic acid, it's not completely clean. Then you got benzoic acid, it's kind of a pain in the ass. Here, the only byproduct is acetone, so it's very, very clean. It's a nice reaction. And you make an epoxide, not a glycal. Notice I'm still drawing this kind of in a chair conformation, or a boat conformation. And that's because it still can't adopt a chair. The epoxides can't do that. If you try and do it with your model kit will break. But you can kind of get it to work in a boat.
Sorry, John. So I just kind of missed what you said about the reaction condition. So is that DMDO, acetone, and then an alkene and
Then, yeah.
Okay.
And or.
Oh, or, okay. Gotcha.
And this is the quench. Just in case any of you guys go out and set up some DMDO reactions tomorrow, I just don't want any of you to blow up.
That's fair.
You seem like nice people. So if you want to make a fluoride out of this, hopefully you're kind of thinking, you've seen enough of these goddamn anomeric things to think, you know what, this is kind of in equilibrium with that. Like, definitely I've drawn these equilibrium arrows equal, and that's not probably very accurate. But you're kind of, like, you have that anomeric center, you have oxocarbenium kind of thing, you have this bond is definitely going to be weaker than this bond. That is definitely the case. So you have something like this. So if you treat this with a really strong nucleophile, so tetrabutyl ammonium fluoride, it's a really strong nucleophile because fluorine is pretty actually decent as a nucleophile. It's hard, it's very small. It doesn't have that big polarization benefit that iodine has, and it stabilizes negative charges really well. But when you're using a salt like this, that negative charge is entirely on a fluorine. That fluorine is entirely naked with that negative charge. It's not masked by a partial positive charge because that nitrogen is surrounded by those big bulky butyl groups that are keeping F minus away from the positive center in the middle of them. And so you have really a naked fluorine. If you have other types of fluorine salts, they tend to make salts. They tend not to be all that nucleophilic. And so you click a button randomly and your slide jumps. Where is my mouse? There we go. So unsurprisingly, this comes from the top face. And that's because the bottom face is blocked by your epoxide. So epoxides give beta fluorides. Okay. What if we want an alpha fluoride? Well, if you want a normal sugar, going through this mechanism, you're never going to be able to get an alpha fluoride on this because the DMDO always epoxidizes from the bottom face. There's one exception. And MCPA doesn't really matter. I don't actually completely understand why. Because to me, we should be getting an anomeric effect, which should favor. Oh, exactly what I've drawn. So no, this is okay. The anomeric effect is the next one. It doesn't make any sense. The anomeric effect would really like that alpha oxygen straight down, right? It's a good leaving group because of that O minus thingy. So that's fun. The exception, and we're not going to encounter it, but I just like pointing it out because it's just weird, is if you use one of these ultrose sugars. I guess it needs to be a glycal. Bulky. PG is protecting group at the C3 oxygen. And it's down. Then you get the up epoxide. That's a lot of special pleating. That is, that's a stupid sugar for the first thing because who wants an axial oxygen at C3? It's not a very biologically relevant sugar. It also needs to be a bulky protecting group. If the protecting group is not bulky, then you still get the DMD, you still get the epoxidation down. The epoxidation down is really, really favored. So getting the epoxidation up is really, really hard to do. But if we do want to get something that's equivalent to that, and this is why I begged off last class. We can use this reagent. So that's a stupid reagent. Hypervalent iodine. So again, let's just take a look at what this actually is because, again, very unusual molecule. And it's because iodine's got all those orbitals. What we have is we have iodine making 3 bonds. which I do not love. It is wrong, but it is true. And then there is some silicon tetrafluoride. So that's a bit weird. And often a bit of water. Which I think is mostly DMF is how you do this. I don't think it matters though. You could use THF. I don't care. Okay. What's the first step here? So if anyone's seen any kind of hypervalent iodine has anyone seen hypervalent iodine chemistry before? Silence. Okay. By hypervalent, I mean iodine is bound to more than one thing. This is iodine 3 instead of iodine 1, which is the way iodine should be. And because iodine should be iodine 1 and not iodine 3, our end goal here is to get the iodine down to iodine 1. We're going to start with an SN2 on iodine. Now, for reasons which in the textbook and the paper I just read are defined as a complex interplay of sterics and electronics, which actually sounds like something I like to say a lot, but I don't think I've ever actually put it into print, which means they don't have a fucking clue. The iodine goes up, not down. And my voice breaking a little bit was an entire part of that process. I'm okay with this mechanistically over why this happens with the up position. And so what we can think about is, and this is me speculating at this point. But I like speculating. So we have a glycal. I don't know. Let's just say there's OAC on every other position. Everyone likes a good acetate. And let's make it glucose. I said glucose. It was galactose, which is a better sugar in every way, but not what I said. Okay, so if we're thinking about where the orbitals are, on this molecule. So we have a double bond here, and we've got the sigma, the lone pair in the oxygen directly adjacent to that. So what we can do is, let's say we're trying to make this new double bond here, which is going to release the lone pair into this orbital here. So we're releasing the lone pair into the C2. Okay, I'm going to redraw that because it's really messy right now. And all I'm going to do is keep track of the fact that everything else is equatorial. I'm not going to draw what they are. Let's just, the substituents are equatorial. We're in the stable chair. This is the chair we want to have because all the other substituents in this twist chair are equatorial. If we draw the other twist chair, which you are welcome to do, all your substituents will be axial, which isn't good. So we want this one. Okay. Now you have a negative charge building on here as you're starting to build this double bond. So that carbon is now moving from being an sp2 carbon to an sp3 carbon, and we effectively have this I plus nearby. Okay. Now, it has two choices how to move that lone pair. It could either attack up or attack down towards the iodine, because the iodine can approach from either the top or the bottom face. Let's say we attack from the bottom face. Bottom makes sense, I draw it on the bottom. So we're in like a full twist boat here. Like a formal twist boat. This is a very high energy conformation. This is actually the highest energy conformation that a six-membered ring can take. Okay, but if instead we attack from the top, then what happens? I'm just going to still draw in the back. No, whatever you did, I didn't want to do that. But now, this front carbon is pushing up, which is going to push this guy down. And oh, look, that's a chair. And chairs are very low energy, as we know. So it's more energy favorable to attack from the top, or to attack the top. Attack up towards iodine. That's not you. Otherwise, it seems a bit ambiguous. And it's the carbon that's making the attack because it's got the electrons, and electrons are violent. Okay, because here's the problem is I have like black panels here, so I can't actually see if I have a whole bunch of blank faces staring back at me. So did that make sense?
I'm kind of confused why the top makes a chair and the bottom doesn't still. Can we just run through it again?
Yeah, no, absolutely. Because if this is good. Good. Okay, so we got a few. Are we good to this point?
Yeah.
Okay, I'm going to start a new slide. Okay. So I'm just going to draw the carbons in the oxygen. Did I just draw the wrong one? Yes, I did. That is the wrong. That's going to give us the bad boat or bad chair, because everything's going to be axial. That's better. So I'm not drawing in double bonds right now. We can sort of think that we have partial double bonds all the way along there, because this, again, what we're drawing is this. And so we have a resonance structure. Like that. So think about that. And so I'm thinking This is going to be the carbon that attacks because this is the carbon that is negative in a resonance structure. That's where the negative charge is. It's not going to be this carbon, because if this carbon attacks, then this carbon would be positive. Let's just think about that. So if we added the electrophile here, this carbon would be positive because we would have had to have used the lone pair of the double bond to attack the electrophile. This oxygen would be neutral, and there'd be no way for them to stabilize it. So that's really stupid. So it's going to be this carbon that attacks. And so there's an electrophile present. It's iodine in this case. And if it's approaching from the top face of this molecule, what happens is this carbon stretches out towards it, is pulled up towards it. Because right now it's shaped like this because we are sp2, sp2, sp2 hybridized atoms. But this guy's going to sp3. And so it's going to bend out of this more towards a chair. And so the iodine is on top. What happens is it gets pulled up. So that carbon gets pulled up, which pushes the other carbon down, which keeps the oxygen up. So I'm just going to label some of the atoms with some color just so we can keep track of which atoms are which. It's really easy. To that. And then that's where the iodide is attached. Whereas if the iodide attacks from the bottom face, this guy gets pulled down towards the iodide. If we do that, that pushes the other carbon up. The oxygen really doesn't move. Nothing else moves. And now we don't have a chair. So if we essentially have a boat. What I want you to do is just change the iodides here. What I want you to do is just change your perspective a bit on this. And I'm just going to add some colors. And we're going to look as if the green bond, we're looking straight on the green bond. And if we did that, what we would see is blue up. And then, no, not subtitles. And then sort of down towards the two orange atoms, one of which is oxygen. No, not that either. And I've drawn that really badly. Actually, I've drawn that so badly, I can't live with myself. Kind of drawn a bit like that, and that's a boat. You kind of have, there's, like if we flip it on its head, like there's this bond here. There's the green. There's the subtitles. There's the blue. So that's kind of boat. Did that help at all?
Yeah, I think, yeah, I can kind of spatially see it now.
Yeah, I think actually if you have a model kit, it's not a bad idea to make, where's my notes?
Yeah, I'll just make a note to make.
Yeah,
make
this
it
is worth
visible.
make a model. Okay. Okay, so, but we haven't really done anything yet. We've added iodine. So let's just go back to what we've done. This is why I think the iodine attacks from the top face. I need more space because we still have other crap attached to that. So we just made that. And that iodine still has an acetate attached to it, and it still has a phenyl group attached to it. Now we just released an acetate. We have some water, and we have some silicon tetrafluoride. This is the second place I don't quite understand what the hell is going on, because to me, silicon tetrafluoride is like the end state of silicon. Silicon loves making bonds to fluorine. They're really, really strong. But it is fully possible that what happens here is a bit of acetate adds to the silicon. And this is a reversible reaction, and I think it lies way towards the starting materials. But you will get silicon with 4 fluorines and an acetate, and I don't care what the geometry of that is. It's some inorganic thing, and it doesn't matter. And it's negatively charged. Now, 99% of the time, what it does, the acetate takes off, but occasionally you lose a fluoride. And as you just said, fluoride is a really strong nucleophile. And just like with the tetrabutyl ammonium fluoride, there's nothing stabilizing it. Like the only actual counter ion for the fluoride is actually the oxocarbenium. Now, we don't have some sort of epoxide blocking the bottom face. And if I ask you to tell me what is the best X group for receiving electrons through sigmatropic donation through the anomeric effect, hopefully you're going to say fluorine, but that's insane. Fluorine is, well, I guess we made some anomeric fluorides, but fluorine is the best electron receiver for this because it's got the lowest lying orbital, because it's the best receiver of electrons, because it's the most electronegative atom. So everything that makes a good anomeric leaving group, or a good anomeric group that wants to sit alpha, like a strong anomeric effect, fluorine's got it. So it's unsurprising that fluorine comes alpha. And if you remember, this whole thing was based around the idea of how do we make an alpha fluorine? Well, we made an alpha fluorine, but we have this stupid iodine thing still attached. Now, this is speculation. The paper and every single book I can find and every single textbook I can find says, well, they actually don't draw any of what I've just drawn. They just draw, this goes directly to the product. That makes no sense. So they really skip over this step. But I think this is a very, very traditional sigmatropic rearrangement. Again, we want to make iodine 1 and still iodine 3. So, you know what? Let's just let iodine take those electrons. If it does that, we just saw with MCPBA that we can get things like acetals attacking atoms. Or rather, you know what? I'm going to redraw that. It's sigmatropic, so the arrows can go both ways, but let's draw the arrows slightly differently. I'm going to steal the electrons from the carbon-iodine bond and attack that oxygen. So I'm using the electrons in the carbon-iodine bond. If I do that, I need to break a bond to the oxygen because there's too many bonds. It's a little weird to be using the oxygen of a carbonyl as an electrophile. This isn't the only mechanism that does it, but it's not that common. And if I do that, that oxygen is going to make 3 bonds. That's not possible, so we'll put electrons back on iodine. So this first arrow here, I was stealing electrons from iodine. With this last arrow here, I'm putting the electrons back onto iodine. And if I follow what that gives me as a product, fluorine, acetate, plus phenyl iodide. Now, I'm a whole lot happier with phenyl iodide than I am with anything else we've seen in the way of iodine sources in this reaction. That one makes sense. It's iodine 1. The iodine is making 1 bond, as it should. And we've just installed an acetate at C2. We've just installed the mannose acetate, of course. But that's what you get. Like, this is the product of the reaction. So all told, what do we just do? Well, we took a galactol. We treated it with, one option was DMDO in water, acetone, made the epoxide, and then tetrabutyl ammonium fluoride it. That is not a verb, but it is now. In the other example, we took the same guy. We used this iodine agent, which as far as I know does not have a name, like beyond its IUPAC name. Yeah, SIF4, that needs to be a longer arrow. Some water, some solvent, or DMF, I think is what I said. And we spat out C2 acetate. Now, under these conditions, it's kind of basic with all the fluorines floating around, the F- floating around. So you actually do partially cleave the acetate. So what you'll find is people always reacetylate under these conditions, but you know what, whatever. We'll see if we get the acetate. So we can make the beta fluoride with an OH, or we can make the alpha fluoride mannose. So let's say we wanted to make, let's say you're just, bored and you wanted to make this guy, alpha fluoride, not mannose. You can't do it going for Nair. The way I would approach this one, just sort of complete the set, is I would have taken the anomeric bromide that we talked about making a couple classes ago, treated that with tetrabutyl ammonium bromide. And what we know is that goes to the beta bromide. And then I would have added a fluorine source in here. So it would have made the beta bromide momentarily. We know the beta bromide is a lot more reactive than the alpha bromide. That's how all that chemistry works. And then the fluorine would come in and displace that and make the alpha fluoride. I'm not 100% sure this has been done, but it'll work.
John, sorry, what? I have a really stupid question, but the very first molecule in the top left, what is that called again?
Glycal.
Glycal. Okay, thank you.
which is actually what I'm going to spin over to start talking about again. Okay, I think I am done with fluorides for now. We talked about how to use them last class. I've got nothing more to add on fluorides, so I'm going to leave them unless there are some questions about them. Besides, oh god, what did I just sign up for? I don't have any answers to that. That's why it's an open book exam. Okay. That was less dramatic than I thought by drawing something instead of changing the page. Nope, stop it. There are days I prefer to be dealing with lab floods than OneNote or whatever program. Sorry, this is PowerPoint. So talk a little bit about glycals and its friends and related compounds. So we've already seen how to make glycals. Again, just as a reminder, if you have one of those anomeric bromides, you can treat that with zinc metal in acetic acid, and the zinc comes in, kicks out the C2 acetate. It doesn't do this in, you know what, I shouldn't draw it like that because it doesn't do this in one step. It can't stereochemically. There, bye-bye acetate. But there are other ways of doing this too. Because the thing there is, if you'll notice, I'm not really closely keeping track of everything else, but let's just do that for a moment. We've stripped away the C2 oxygen. Like we've lost that. So we need to, if we want a sugar, we're going to need to put it back. That can be useful because maybe I don't want an oxygen there. Maybe I want a nitrogen or a sulfur or a halogen like iodide or fluorine or bromine or just hydrogen. In which case, getting rid of that C2 oxygen is actually kind of handy. But often I'm going to want it there. And so let's just think about a slightly different set of conditions. Now, I'm going to admit that zinc thing is fucking weird. That is not normal molecule things doing what molecules are supposed to do. It's metal stuff, and metal stuff makes me nervous. This is completely normal chemistry, though. I promise. So I take that. I treat that with Tetrabutyl. I really want to draw NU, but I really mean Bu for bromide. A little bit of collidine. And ethanol. One equivalent catalytic solvent. Okay. Anyone want to think about what's going to happen first?
Do you switch to the beta bromide?
Perfect. There's a catalyst. It's there for a reason, and often the first step of a reaction is the rate determining step. And so we've seen that this catalyst, in the presence of an alpha bromide, switches us to a beta bromide. So absolutely. Okay. Now I've drawn this acetate here not just for shits and giggles. There must be a reason. What happens now?
Do you
Apparently,
get
Samara drops the class. Okay.
I was gonna say, do you get nucleophilic attack from the carbonyl?
Yeah, exactly. Okay, we can get that. Now, this is a bit weird. I'm just going to give it because depending on the conditions, so I know that this can't be the complete mechanism, and something much funkier is going on because if I leave off the colony and I treat this with ethanol, ethanol would come in beta, and we would have the beta ethoxide, and that's not what we get. So something is going on a little bit with this colony, and I don't quite understand. But that's just what else is new. So might be more of a reaction rate thing. Just we don't normally think too hard about this happening, but there's nothing stopping it. The ethanol, instead of attacking the carbonyl or the carbon of the anomeric center, it attacks the positively charged carbon, which makes a lot of sense. And we get this molecule. Now, note that we have a carbon with 3 single bonds to oxygen, and I've been repeatedly saying that I am very uncomfortable with a carbon with 2 single bonds to oxygen. So you can imagine what I think about a carbon with 3 single bonds to oxygen. It's not much. This is called an orthoester. Ortho kind of being like different or nearby. And it's an ester because ester carbon makes 3 bonds to oxygen. So it's a 3 bond to oxygen, but it isn't like a normal ester. It's kind of a orthoester. It's a nearby ester, but it's not an ester. Okay. Now we have a base. Anyone except Paul want to guess what the base does? You can take this 2 steps. So you can say the first step and then shut up and not get called on. Like the conceptual step of what a base does. Ashley, what do bases do?
Would this one like do anything with the nitrogen?
Well, the nitrogen is basic.
Okay.
So what does a base do? If I say what like bases there, it's like saying that somebody is a skateboarder. What does a skateboarder do? I don't know why I said skateboarder. Like, what is the unifying factor of all skateboarders?
I'm so confused with the skateboarder.
Sorry, okay. Bases are bases. They take protons.
Yeah.
That's what they do by definition. So I said it's a base, so it's going to take a proton. So we need to find a proton. And remember, we're talking about glycals. So does anyone want to guess what proton we're going to find if we're talking about glycals? We're almost there.
Would it be the C2
Yes.
hydrogen?
Perfect. Like, look at this. Like, look at that angle. I'm getting like all really excited in completely inappropriate ways from this anti-periplanar orientation between a hydrogen and a leaving group. Like, this is an E2. This is just E2 chemistry. For all this weird shit we've seen today of atoms doing things they shouldn't be doing, this is just E2 reaction. Ethanol comes in, ethanol goes out. You know, that's what ethanol does. We could even leave it positively charged here and make ourselves happy by having that proton still on there. Just pretend it never came off. There's northwester, temporary, boom, forms, E2 elimination, gone. And our product is a glycal. That's just like a really good drawing of a book. I will never be able to do that again when I'm trying to draw a book. But we didn't lose our C2 oxygen. We still have our C2 oxygen. We've just lost our C1 oxygen. So we have a way here with the zinc acetic acid way to get rid of that C2 oxygen. But we have a way too where we can use these bromides and we can keep the C2 oxygen. But this, of course, only works if you have an acetate. If you don't have an acetate at C2, this doesn't work because then there's no acetate to make the orthoester. So like benzoate as well, any kind of ester would do this. But we're going to be talking about reasons why we're not always going to want acetates on places. So is there another alternative? Let's say, and again, this is going to be the recorded lecture I'm going to do because on, you know, I'll try and put it up. Maybe I'll try and do it over the weekend or early next week, not over a reading week, and try and get it up there. And it's just protecting groups. I don't think there'll be many questions, and so I can probably just go ahead and do it. And it might be a little bit longer, and maybe what I'll do, what I'll do is I'll break it up into like sub lectures, so you can go and look at specific things or run them all together. Samara is now running my YouTube channel, and so maybe she can figure it out. I have this fancy video editing software on this laptop. I haven't really figured out how to do it, except how to silence things, so that there was a presentation going on for one of my students in group meeting, and we used that presentation video in a paper. But the problem is we included the whole video and it has the audio. And so you have this audio while the video is going on, and the audio has absolutely nothing to do with the video. It's completely appropriate language and things. It's talking about cannabis. No, it's not talking about cannabis because the video is about cannabis. It's talking about something that isn't cannabis. I think cancer, like, you know, something inappropriate. And so our cannabis video is contaminated with this cancer talk. And so I had to use this software to delete the audio, but it allows me to like delete stuff and include stuff. And I guess if I really cared enough, I'd edit these videos, but I really don't. That just takes too long. Okay, so I'm just highlighting the atoms that are going to be involved in this. We're going to come back to this thing. This is a glycosyl sulfoxide. You're going to love them. We're probably going to do them next class. And I've never really figured out how to teach this glycal stuff because it ties in with the fluoride, but it ties in with the sulfoxides, but it ties in with the halogen bromide stuff. And, you know, glycals are like the great intersection of all the different things. But take it for granted that you can make glycosyl sulfoxides. And what you can do with this is notice that we have benzyl protecting groups everywhere instead of acetates. And we just heat it. We just heat it. Then what you have, again, is just think about what your shape here. Nature loves 5-membered rings. 1, 2, 3, 4, 5. So I'm going to change my color of my ink to... No, I'm not brave enough to use the bright yellow. I'm just not. The sulfur oxygen grabs the hydrogen, which makes double bond. Sorry, that's a positively charged sulfur, which pushes the electrons onto the sulfur. Oh, look, we just made glycal. And this time we can make a glycal with benzyl protecting groups. And at this point, you're going, why the fuck should I care about that? And I promise you will care because it's important for your grade. I promise you won't care for any other reason. Sarah might care because she might actually have to do chemistry with this. But we can make these kind of all benzyl glycals. Okay, so now we have seen a whole bunch of ways to make glycals. We can make glycals such that we lose the C2 position. We can make glycals such that we can keep the C2 oxygen with acetate protecting groups. And we can make glycals such that we can keep the C2 oxygen with a not acetate protecting group. I use benzyl here. You could have used anything. Like almost any protecting group would have worked.
Would the acetyl groups work?
Yeah, they do work okay. You do run a risk of having other thermal eliminations occurring with acetyl because it's a good leaving group. But it does work too with this, yeah. I've had it happen to me by accident with acetyl groups, with sulfoxides. It's frustrating when you don't want a glycal. You wanted something else, and it made a glycal on you. So yes, acetyl groups do work. I wish they didn't. So this is going to be the one time I am basically going to say I don't understand this at all. And I'm going to make well, it's also going to be the one time I'm going to be completely simplifying something and lying to you. So if we take a glycal, it's said to be very well understood. And I think I have to maybe catch up with some reading because it didn't used to be. But there's been some recent stuff that's come out in the last year where people have been saying the mechanism of this a little bit better. But it's still kind of hocus pocus magic to me. So if you take a bunch of different reagents, so this isn't, again, I'm not quite true. I'm going to stretch the truth here, but it's mostly true. So I don't know if you've seen this reagent. It's called NIS, N-iodosuccinimide. Beautiful, beautiful crystals, crystallizes out of water. Wonderful stuff. It's a source of I+. Basically, that nitrogen iodine bond, if you see a bond that you're not used to seeing, it's probably because it's weak. There's not a lot of it in nature. So nitrogen iodine bonds are very weak. And so unsurprisingly, we're going to break it. And we're going to push the electrons towards nitrogen. And that's because nitrogen can take those electrons and throw them into all sorts of resonance with those carbonyls right next to it. So it's a source of I+. So we get this. It's a source of I+. And what we're doing is top iodination. So for the purposes of this course, NIS gives you iodination from the top face of the molecule. Similarly, NBS or NCS, which is the chloro or bromo versions of this, also give you the top. Now, if we think about what those are going to do, I've drawn them like that. This is obviously a resonance structure for this, or it's an equilibrium if you prefer, because I'm going to, I'll flip. No, I guess we can draw resonance structures, sigma resonance, where we can break that bond and have our oxocarbenium. So we've taken this galactol and we've turned it into an oxocarbenium. And now we have a halogen at C2. And I'm going to put this in brackets. You could have something here or not, depending how you made your glycal. It doesn't change the outcome of this reaction. You still have top or bottom. You just have that, a hydrogen or an acetate, depending if you made the glycal through the zinc or through the other two mechanisms that we showed, or a benzyl group. It can be any of these things. All of these work. Okay. Now, if you want a bottom halogen, then use a different reagent. And this, again, that top one makes sense. That is the same argument we just used for all these, the hypervalent iodine that we talked about. It drags up because it goes through a chair transition state. That's why we want to grab the iodine from the top phase, chair transition state. I don't understand why this one works. So this is IDCP. What the fuck is IDCP? I'm only going to draw it once. Pyridine, except it's not pyridine. It's normally this is called collidine. It's basically pyridine with some methyl groups. I don't know why they give it a special name. Lutidine is pyridine without that back methyl group there. Fine, I guess. Sandwiching an iodine ion, I plus ion, between two of them. Now you're understanding why no one wants to draw this. And it's the perchlorate salt, which is a really, really poorly coordinating ion. So iodine chlorate, I don't think that's a thing, actually. I don't think that's a stable salt. It probably blows up. A lot of perchlorates blow up. So I imagine this one does too. So this stands for iodonium dicollidine perchlorate, IDCP. That's a mouthful. Who cares? I'm going to call it IDCP. You take that same glycol we have up there, ditto, and by the magic of chemistry, you mostly get the down iodine. There is no equivalent from bromine. So this is an iodine specific kind of thing. And again, you could or could not have an acetate there. It doesn't matter. But you have the oxocarbenium. with a down iodine. And it's up to you if you want to have an acetate there. I guess I probably shouldn't have not had it here. It's just really crowded. I really hate drawing Manos chip boats. It's one of my least favorite things in the world, along with nails on a chalkboard and my dog whining at 3 a.m. Okay. So we can have up halogens, we can have down halogens, and we can do it by choosing what reagent we use with the glycal. Okay. Why do I care? Why is this important? Well, let's just think what we could do with this. So I've been really cagey about activating all these things and what the chemistry is, but let's actually just do something with this molecule. So we got a glycal. Let's say we treat it with IDCP. We're going to make intermediate A. We're going to not isolate. We're just going to stir it for a bit. And then we're going to add another sugar. You know what? What we can actually do is we can go all Samuel Danishevsky on this thing. You know, I shouldn't say that. The guy's an asshole and probably involves doing something worse. Yes, Samra, I think it is a complex interplay of sterics and electronics. Size definitely comes into it. I think it's the way this thing is delivered. The pyridines never completely dissociate, so I think there is a size function over why that's being delivered from the bottom face. It's also possible that you don't really have an I+, so the mechanism of attack might not be nucleophilic. It might be single electron transfer reactions, in which case you don't really have electrophile-nucleophile interaction, and so you're not really doing that electrons from the sp2 shifting to sp3 at that center all in one time. I can wave my hands around a lot to try and justify that, but I don't think the control reactions have been done with enough things to nail that down, and I'm not sure, to the best of my knowledge, the computational chemistry hasn't been done. And I guess we could do that. No, I've got way too many things on my plate. This doesn't matter that much. It works. No, down.
Get the spray bottle.
Yeah. Okay, so we basically, the entire idea of these things is so we get 6 sugars together. We've really avoided that. I've been using ethanol as my nucleophile, but there's nothing stopping you. You know, a sugar is just like, that's just ethanol with like a lot of shit attached to it, like this other sugar. So if we do that, what we're going to get is a down iodine, because it's IDCP. We're going to get a beta attack because it's going to attack opposite the iodine, right? Like you have the iodine sitting down on the bottom, and then you get the attack. It's like anchiomeric assistance, both in iodine instead of an acetate. I just really want to draw a chair. That's all I want. I'm drawing too many effing boats. I'm really bored of boats. So what we've done there is we made a disaccharide, right? So we took the glycal, we treated it with IDCP, we got the down, A is the down iodide. Good mechanism maybe to practice. Then we took that and we attacked that with the other glucose. And you know what? We probably threw in a base in here. My favorite base for all of these things is Hoenig's base. I like calling it Hoenig's base because Hoenig doesn't get enough credit for this, and he should. But the big thing You know what? I don't know. Maybe Honig was a she. I really need to look that up. Mostly as German chemists, where it was like really, really male, but we do chemistry. Actually, there are a bunch of named reactions named after women. They're kind of almost erased because we've only left it with the last name, and then everyone assumes it's a man. Anyways, probably named after a male German from the 19th century, but it might be named after a female German from the 20th century. I just don't know. Or we're also going to call it diisopropylethylamine because it's diisopropyl ethylamine, DIPEA. It's my favorite base because it's really, really bulky and it never does nucleophilic attack. Triethylamine does do nucleophilic attacks, especially when you don't want it to. DIPA never does nucleophilic attack, and I can say that I've never seen it do one. I'm sure there's some asshole in the literature who has just proven that it can do it if you choose the right electrophile, but we shouldn't give them any attention. Under normal circumstances, it doesn't. So it's just going to mop up extra hydrogens, and the extra hydrogen I'm really thinking about is this guy over here. Once we do if you draw the mechanism of this, and I really encourage you to go home and do that and try that after class. Okay, so Paul looked it up. Honig is a guy. He's got an umlaut over the U, and that's pretty cool. I like umlauts. So we can make a disaccharide like this. And we still have an iodine attached. But this actually gives us a lot of flexibility because there's stuff we can do with that iodine. So one of the things we can do with that iodine is we can rip it off. So if we take that and we treat that with silver nitrate and acetic acid, sodium acetate, I'm going to paraphrase the molecule above because I don't want to draw the whole thing, and we are running out of time. But just from that Koenigsegg that we started the whole course with, we know that halogens love themselves some silver. And this is not that silver 0 that makes that soft bond. This is that silver 1 that makes that hard bond. And so we can't make an oxocarbenium here, so it's not going to fall off because it's at the C2 position. But we can really start to lengthen this carbon-iodine bond. Weakens. And we have acetate. So we have an iodine which is halfway gone, and we have a half-decent nucleophile. So we can do SN2 chemistry. And so we can get the manos here, right? Because we're going to invert the chemistry. So if we start with the alpha, with the down, it's not alpha, with the down iodine, like the iodine in the glucose conformation, then we end up with the acetate in the mannose conformation. So we're at 522. That's the end of the class for today. We're going to come back and we're going to talk about how you can retain configuration. So you can replace that iodine with an oxygen and keep it at the same point. We're also going to talk about how we can install some nitrogens using the glycal. No, you know what? We'll hold off on nitrogen. We'll come back to nitrogen and sulfur later. But we're going to use glycals to introduce nitrogens. But okay, so we'll show how to retain it and we'll show how to get rid of it altogether. Though, if you want to get rid of it all, yeah, that's important. Yeah. I think that's it for today.
Sorry, so is that up Words. Is that up facing acetyl group, the new one that we just added?
Yeah.
Okay. Just
Yeah.
wanted to make sure.
Yeah, so that's replaced that. So we could draw it on here, kind of a nucleophilic attack. That's just an SN2. Okay.
All right. Thanks, John.
Have a good one. I'm going to post, yep, see you, Susanna. Thank you. I'm going to post assignment 2 up as well. Okay, take care.
Thank you.
Thank you.
John, do you have a minute?
Yeah, I do.
Oh, Paul's gone. Actually, we had decided that we would ask about the review article. So
Oh,
maybe
okay.
next week then. Yeah,
Okay.
I guess they had to go.
So,
All right.
yeah, Susanna's checking on the flood.
Yeah.
Um,
Why actually do our labs get so frequently flooded? Like, what really happens?
I don't know if it's all that frequently, to be honest.
I don't know. I am in the group for the last like 2 semesters, and it's third time.
Yeah,
It's
that sounds about
being
right.
flooded.
Yeah,
Yeah.
you know,
That's quite a lot.
floods happen a lot. This one, but I think this is like a entirely contained flood within a fume hood.
Oh, okay.
But it's still what, like, flood is a generous term. We've had a lot of pipe. We've had some pipes break. We've had tubing pop off. We've had, but we've never actually had real destruction from any of our floods. We've always
Oh.
caught them. They've never really been damaging. But a flood is anytime there's water where you don't want there to be water, right? So our definition of flood is pretty elastic, and I tell all my undergrads this, but I tell the grad students this too. Like, you're a real synthetic organic chemist when you've had a fire, a flood, and an explosion.
Interesting. That's nice.
So I've had many of each. Most of the explosions are just like the reaction explodes. Like, you don't have like a fireball or anything. It's just your reaction mixture explodes all over the place, and suddenly you're cleaning it up inside of your fume hood. Because those mistakes happen. They just do. This shit happens.
Yeah, they're unavoidable.
Yeah. I like telling myself that because the worst flood I've ever been involved in or I've ever seen was I caused it. And the second worst flood I've ever seen, I also caused. So I like to think there's some value in learning from flooding labs.
So you kind of encourage flooding labs.
Well, I'm not going to say I encourage it, but I am going to recognize that you can be a very, very good and competent chemist who floods labs occasionally.
Okay, all right. So that's something we should put on our CVs, right? Not well applying for jobs. Yeah.
Okay, I'll talk to you later.
Yeah. Thanks, John. Bye.
Okay, bye.
Take care.